This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 7 of Week 3, Forced Convection. The Nusselt number correlations for flow inside a tube and over a flat plate, the hydraulic diameter for non-circular ducts, and a worked solve for the exit temperature of water in a heated tube. Every forced convection problem is the same four-step recipe. Newton's law of cooling is the anchor. Q dot equals HA delta T, but the exam rarely hands you H. Step 1. Classify the flow from the Reynolds number, internal or external, laminar or turbulent. Step 2. Pick the matching Nusselt correlation. Step 3. Back out H, Nusselt times conductivity over the characteristic length, the diameter inside, the plate length outside. Step 4. Use H in Newton's law, or close an energy balance for the exit temperature. The whole topic is correlation choice and property temperature. Same three-column shape as the other Week 3 decks. Reynolds and Prandtl set the correlation. Nusselt is what it returns. Conductivity, viscosity, and specific heat are fluid properties. H is Nusselt times conductivity over the characteristic length. And the bottom rows are mass flow rate and heat transfer rate. The make-or-break detail: external flow uses the film temperature, the surface free stream average. Internal flow uses the bulk mean, the inlet-outlet average. The wrong reference throws off every property, and therefore H. Internal flow. The Reynolds number uses the mean velocity and the tube diameter, but for a known mass flow rate, the handier form needs no velocity. 4 m dot over pi d nu. The exam usually gives mass flow, so reach for that. Now classify. Reynolds below 2300 is laminar. Above 10,000 is turbulent, where Cedar-Tate or Dittus-Boelter applies. In between is transitional. Dynolinsky territory, out of NCEES Handbook scope. Textbook reference only. Laminar tube flow is the easy case. The Nusselt number is just a constant, with no Reynolds or Prandtl dependence. 4.36 for uniform constant heat flux, 3.66 for constant surface temperature. Which one? Read the boundary condition. An electrically heated wall is essentially constant flux. Condensing steam or a phase change bath is essentially constant temperature. Memorize both. The only trick is matching the boundary condition. The handbook also prints a combined entry length form for flow that isn't yet fully developed. Turbulent tube flow. For Reynolds above 10,000 and Prandtl above 0.7, the handbook prints the Cedar-Tate form. Nusselt equals 0.023 times Reynolds to the 0.8 times Prandtl to the 1/3 times the viscosity ratio to the 0.14. That ratio corrects for the bulk to surface property difference. When the wall to bulk difference is modest, it nears 1 and is often dropped. Drop it and swap the 1/3 exponent for n, and you have the textbook Dittus-Boelter form. N is 0.4 for heating, 0.3 for cooling. External flow over a flat plate. Evaluate fluid properties at the film temperature, the surface free stream average. The handbook gives the average Nusselt in two pieces. Laminar below 10 to the 5th, 0.6640 times Reynolds to the 1/2 times Prandtl to the 1/3. Turbulent above 10 to the 5th, 0.0366 times Reynolds to the 0.8 times Prandtl to the 1/3. Note the handbook's transition is at 10 to the 5th, and its turbulent coefficient is 0.0366, not the textbook 0.037. Non-circular ducts. The internal flow correlations are written for round tubes, so for a rectangular, annular, or other non-circular duct, replace the diameter with the hydraulic diameter, 4 times the flowing cross-sectional area over the wetted perimeter. Everywhere D appears. Sanity check. For a circular pipe, it reduces to exactly D, as it should. One filing note: hydraulic diameter isn't in the heat transfer chapter. It lives in the fluids chapter. Worked problem. Water flows through a 20 mm tube at 0.20 kilograms per second, entering at 20 Celsius. The wall adds heat at a steady total rate of about 3,930 watts. Water properties are given at the bulk mean temperature. 2 parts. First, confirm turbulent flow and estimate H. Classify the flow first. The mass flow form of the Reynolds number, 4 m dot over pi d mu, is around 11,400, above 10,000, so turbulent. Apply Cedar-Tate or Dittus-Boelter. The water is being heated, so N is 0.4, and Nusselt is about 83.7. Back out H, Nusselt times conductivity over the diameter, roughly 2,500, typical for liquid water. But the key point for part B, the exit temperature doesn't need H at all. It falls straight out of an energy balance. Now the energy balance. The heat added raises sensible enthalpy, so a steady flow balance gives Q dot equals mass flow times specific heat times the temperature rise. Solve. Delta T equals Q dot over m dot Cp, about 4.7 Kelvin. Added to the 20-degree inlet for an exit of about 24.7 Celsius. Notice H never appears. It sets the tube length you need, not the exit temperature once the heat rate is fixed. Final answer. Exit temperature about 24.7 Celsius. A rise of roughly 4.7 Kelvin. 4 checks. Units. Q dot over m dot Cp gives watts over watts per Kelvin, which is Kelvin. Magnitude. Run it backward. That rise demands about 3,930 watts, exactly the heat input given. Property consistency. The bulk mean is about 22.4 Celsius, where the properties were evaluated, so no iteration is needed. Regime. Reynolds and H confirm turbulent flow, but the exit temperature stands on the energy balance alone. 5 traps that cost points. 1. Wrong reference temperature. External flow uses the film temperature, internal the bulk mean. The wrong one shifts viscosity, conductivity, and Prandtl, corrupting H. 2. Wrong characteristic length. The diameter for a tube, but the plate length for a plate. A silent order of magnitude error. 3. Wrong Prandtl exponent in Dittus-Boelter. 0.4 for heating, 0.3 for cooling. 4. Using a turbulent correlation in the transitional band. The simple correlations need Reynolds above 10,000 or below 2,300, with Gnilinski in between, out of handbook scope. 5. Reaching for H when an energy balance suffices. An exit temperature question often closes on Q dot equals m dot Cp delta T with no H, so compute H only when asked. Bookmark the pages. Newton's law of cooling, the internal Reynolds number with its mass flow form, laminar tube flow, 4.36 for constant flux, 3.66 for constant temperature, turbulent tube flow, flat plate external flow, and the film temperature all sit on 3 consecutive printed pages, so one tab covers the topic. The lone outlier is the hydraulic diameter back in the fluids chapter. Tab it separately. And Gnilinski isn't in the handbook, textbook reference only. Up next, Topic 8, Natural or Free Convection. Topic 7 had a pump or fan driving the flow. Topic 8 removes the pump. The flow is set in motion by the temperature difference itself, through buoyancy. We'll meet the Grashof and Rayleigh numbers that replace Reynolds as the regime setter, the vertical plate correlation, and how to tell whether a problem is forced or free. See you in Topic 8.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.